Okay, we are recording, but let's see. I haven't brought up this software in a long time. Seems like. Okay, go ahead and click in for attendance. Everybody click in. Yes. No. Fall? Cal 1 most likely. Whoa, what happened? What the hell happened? Okay. We good or not? Everybody's clicked in? I don't know what's happening there. All right. No, wrong one. Where was it? Chapter F. Where was it? 1414. Okay, let's get started. This is where we left off, right? And yes, I think they're in that filing cabinet over there. If I have them, they're over there. Remember, if you miss class, I post the notes, so just print them off and bring them. Okay? Future reference. All right, which of these did I do? Did I do any of these? Factor these? I did A? Okay. I can look pretty easily here. We did A? And B? Yeah, we did B. I did this one. Okay, so let's move on to bigger and better things. Okay, so what I want to do is I want to pick up with number C. Yes, number C. With letter C, but I want to do something a little different. Okay? The whole goal of last class was to figure out a way to factor these things, right? Because y'all are saying no already? Okay. Because we wanted to be able to sketch them, right? Okay, so what we're going to do is, I don't know how many of these I'll do. We'll see how comfortable you feel with it. But I'm going to do this part C, but I'm going to start off with the instructions that you would have on a test, which would be sketch this polynomial. We'll go through all the steps. Within those steps is going to be where we're going to have to factor it. Yes, I did. Yep. Just let me know at the end. Okay, so you ready? I want us to sketch the following function. F of x equals x to the 6th power minus 3x to the 5th power minus 11x to the 4th power plus 3x cubed plus 10x squared. What is this? What is that? Get out of there. All right, that's what we want to do. Now, do you remember the steps for sketching these things? You should have these in your notes. It's in 5.1. Here they were, 5.1.8. Make sure you're looking at a polynomial, determine left right-hand behavior, find the X-intercepts, find the Y-intercept, determine multiplicities of the zeros. So if you know if it's bouncing or crossing, plot the X and Y-intercepts, sketch the left and right-hand behavior, and then connect everything together with a smooth continuous curve, right? All right, so that's what we're going to refer to. So part A, do we have a polynomial function? Yes. Part B, determine the left and right hand behavior of this thing. So it's a degree 6 polynomial. It's an even power. The leading coefficient on that is a 1. So you go off of that table that we had, both sides go up. Okay, so it goes up on the left. In the middle, we don't know. It goes up on the right, guaranteed. Okay, so that's part B. Part C, X-Intercepts. So here comes the hard part. So for the X-Intercepts, we set the entire function equal to 0. So x to the 6th minus 3x to the 5th minus 11x to the 4th plus 3x cubed plus 10x squared equals 0. And now we see if there's a way that we can factor it. So what is the first step for factoring anything? Anything? GCF, greatest common factor. See if there's something that's common to all the terms. They all have an x squared, right? So let's pull that out first. X to what? 4th minus 3x to the 3rd minus 11x squared plus 3x plus 10 equal 0. Okay, so we have started the factoring, right? But we still have this big ugly thing in the parentheses. So we look at it, we say, okay, how do we factor this? Well, 1, 2, 3, 4, 5 terms. Grouping only works with 4, and we saw last class grouping sometimes doesn't work. So we never had anything in a previous class to this to factor 5 terms. So we're stuck. So the only thing we can really pull out is the rational zero test and the synthetic division and making that list and all that stuff. Okay, so that's what we're going to do. So I'm going to focus all of my attention right now on this piece, but do not forget the x squared is a factor. It's one of the big mistakes students make. They get so caught up in everything else, they forget that they pulled an x squared out at the very beginning. All right? So how do I work with this yellow piece here? How do I come up with that list of numbers? Take the 10. Okay, so we look at the 10. We list all the different ways you can multiply two nice numbers and get 10. So 1 and 10, 2 and 5. Is that it? That's it. Those are the only factors of 10. Then we're supposed to look at what after this? The number in front of the, not the x squared. The x squared is not part of what we're looking at right now. The x to the 4th. Was there a number in front of it? 1. And when it's 1, we like that because that means this is our list and we don't have to do anything else. With me? Okay. So now let's start using synthetic division and hope that one of these works. So here comes my synthetic division. Did you find the notes over there? Yes? Okay. All right, so what are the numbers I put in the synthetic division box here? 1, -3, -11, 3 and 10. And we do not have any zeros in there, right? So there weren't any missing x's. And what should I start with on the outside? Either one, right? You pick either positive or -1. I'm going to start with +1. And then here I go. 1 drops down. 1 times 1 is 1. Add straight down here. -2. Multiply 1 times -2, put it here, you get -2. Add straight down, you get -13. Multiply, is this going to work the first try? -13. Add down, you get -10. Multiply, -10. Add, you get 0. That's nice. Okay. And remember what I said on the test. Put this list in order from smallest to largest. Always start with your smallest, and I said it would happen within the 5, 6 tries, right? Usually it'll happen within the first 2 or 3. Okay, so the important thing now is to try and, from this, determine what does this give us, right? That's the important thing, is being able to convert this into some meaningful information. So what does this 1 tell me I have? An x minus 1 factor, right? So I can say x minus 1 And then the rest of the numbers there represent the remaining part that I'm going to still have to look at, and it represents the coefficients, right? Starting with what power of x? X cubed, because the yellow thing up there was to the 4th power. Once you do the synthetic division one time, the power will come down by 1, so this will start out 1x cubed. 1x cubed is just x cubed. Then the powers go down, negative 2x squared, then minus 13x, then minus 10. And then we run into an issue. What's that? That x squared. Now, would you like to bring it down now? I have no problem bringing it down now. Trust me. The more we remember that it's there, the happier I am, right? So x squared came down. This yellow thing turns into this thing. So I'll highlight in yellow, right? This yellow thing turns into this. Okay. Now, looking at this parentheses, we say, okay, 1, 2, 3, 4 terms, maybe grouping will work. It doesn't, okay? It does not work. So you have to go back, exactly, back to the drawing board. But there's good news here. The good news is you do not have to recreate a new list, all right? The list that you had is the same list that you'll have for this new one, guaranteed. All right? You'll follow that? Because the factors of this are the same as the factors of this, right? It's not necessarily because it's 10, it's because whatever broke this down, whatever numbers break this down also break this down. So, or could. The numbers that could potentially break this one down are the same numbers that could potentially break that down. So the question becomes, I'm going to set up synthetic division. I'm going to use the same list. Where do I start? So your instinct would be -1, right? Because we already used 1. You could actually have 1 work again. It could happen. So the rule of thumb is this. We're going to start a new synthetic division box. Okay? And I'm working on this piece that I'll put in green there. That's what we're working on right now, right? I'm going to start with the same number that worked, and I'll continue my list. Does that make sense? So let me try and recap that. We had the numbers 1, positive -1, positive -2, positive -5, and positive -10. That's what we had, right? Let's just say that we had done a problem. We had tried 1, and it didn't work. Then we tried -1, and it didn't work. Then we tried 2, and it did work. Then on the next synthetic division, we would start with what? 2 again. And then if that didn't work, we go to -2, and then we would go to 5, and then -5. So it's just because, remember how look, I don't want to overdo this, but if 1 works again here, wouldn't that give us another x minus 1? So we'd have an x minus 1 squared, which would mean we have a multiplicity of 2, which means it would bounce there. So you have to always keep that in mind, that you could have a repeated factor. That's why we have to try again. I hope that makes sense. Yeah? Just always start with what worked, okay? Don't go back to the one that didn't work, though. If something didn't work, don't try it again, because if it didn't work originally, it's not going to work now. Okay, so I'm going to pick up with 1 again. What goes in on the inside of this? 1, -2, -13, and -10. And let's see. I'm going to work on my own here. 1, -1, -1, -14, -14. That does not give me a remainder of 0. Go to the next one. So we try -1 next, and we continue this, and we hope it works eventually. Okay. Okay. Let me get to that. Hold on. So -1 would be my next candidate, and it works. Now, one of the most common mistakes I see on tests is that students work through this synthetic division, they make a mistake in there. And so they miss one of the ones that works. And then they're like, you promised me it would be in the first 5 to 6 tries. And I'm like, well, because it would have worked had you not made that mistake. So you have to go quick, but you need to be meticulous about it. Like if it doesn't work like this, if it doesn't work, just go back and double check it real quick. Make sure you did all the multiplication and signs correctly. Any questions? Okay, I'm out of space. So I'm going to take everything here and move it to the next page. Okay, so what does this tell us we have? This gives us x plus 1 as a factor, right? Always opposite of what you see. Then the remaining piece is going to start off with a 1x squared, because the thing we were working on was the green one was cubed. So this will be x squared minus 3x minus 10. And then what did we still have in front of that? X minus 1, we'll go ahead and bring that down. And then in front of that, we had the x squared. All right, let's take a quick poll since I brought this today, whether or not you're good with this or not. What's that? Okay. All right. So now what we need to determine is whether or not we can keep, if we need to go again and do more synthetic division, or whether or not we're good to go. So in this parentheses, this is a quadratic trinomial, and this is something I expected everyone could factor walking into this class, right? What does it break down to be? Minus 5 plus 2. So if that breaks down to be x minus 5, x plus 2, can you tell me what numbers would have worked with synthetic division? What numbers would have worked? 5 and negative 2 would have actually worked. And to prove that to you, if I just take this over here and just do a quick synthetic division box, 1, negative 3, negative 10 right there. And then if I would have continued with my list, I would have tried negative 1 again. Wouldn't have worked. I would have tried 2. It wouldn't have worked. But when I got to negative 2, watch what happens. 1, negative 2, negative 5, 10, 0. And then that gives me what 2 factors? X plus 2, and then this one, x minus 5. You see that? So, I mean, I said last class, I think that we should be teaching to factor this, you know, at least showing students this method earlier, because it's pretty quick and easy. Okay, so are we done? I mean, we have the whole thing factored, don't we? X plus 1, there it is. That's factored. Okay, so I'm gonna start a new page so that I can get everything in order here. I was trying to do part C. I was trying to find the X-intercepts. And what I determined was setting the function to 0 was the same as setting x squared. I've already forgotten. X minus 1, x plus 1. X plus 5, x minus 2. X minus 5, x plus 2. Thank you. Equals 0, right? So that's where I am. All that work just to get that. And now I set each factor equal to 0. So set this to 0, set this to 0, set this to 0, set this to 0, set this to 0. What are our solutions? So what's this? What does this give us? If you set this to 0, you get an answer of 0, right? The only thing that you can square and get 0 is 0 itself. Set x plus 1 equal to 0, you get x is positive 1. X minus 1 is 0. Set x minus 1 equals 0, you get x equals 1. Set this one equal to 0, you get negative 1. And then this one equals 0, you get 5. And this one equals 0, you get negative 2, right? Yeah, you're asking, should we have 6 because it was a 6-degree polynomial? Well, we have 5 different ones, but one of them is a repeated factor. So, you know, we know what's going to happen here, right? The squared, we know that we're going to actually bounce there. So, good question. All right, so where are we? Find the Y-intercept, part D. For the Y-intercept, this is the easy one, right? Just plug 0 into the function. If you do that, you're going to get 0. So 0, 0 is a point on our graph, right? Plug in 0, it spits out 0. Part E, what's E? Multiplicities. So determine the multiplicities of the zeros. So let's list these zeros out again. 0, 1, -1, 5, and -2. Ooh. Now tell me what the multiplicity is for this 0 right here. So you go up to it. Where did it come from? It came from this. You look at the power, right? The power is even. Even means bouncing or touching the x-axis. So because of that even exponent, this is going to touch here. Now, where did the 1 come from? The 1 came from this factor right here. What's the power on this factor? It's 1. In fact, all of the other factors are to the 1 power, right? Which means all the rest of the x-intercepts will have the same thing happening. Cross, 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 right? Cross, 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 cross. Quick vote. You like bounce? Go ahead and put bounce instead of touch. I was looking at the Northwest Vista's main website today, like right the main page, and it had a picture of sandals and like a sun, and it was like spring break. I'm looking outside. I'm like, okay. Wishful thinking, I guess. Okay, what's next? Plot the x-intercepts and y-intercepts. So just now we're starting to put the graph together. I'm going to try and put it all right here. This does not have to be perfect, okay? Because we already know that we don't know how high the thing goes and low. We just know where it hits the x-axis. So let's see. X-intercepts, I have one at 0. I have one at 1. I have one at -1. I have one at -2. I have one at 5, which is way out here. See, notice I didn't even put like, 2, 3, 4. I didn't even put that. I don't care to see that on your stuff either. This is fine. Just make sure they're in the right order, right? Don't put -2 over there. Okay, after you plot the x and y-intercepts, y-intercept was already there. What comes next? You connect them, but first the ends come next. The ends will tell you everything. You have to have gotten that right. So the ends are supposed to go up, aren't they? So very lightly, I'm going to write like this. Very lightly, I'm just going to kind of sketch. This side's supposed to kind of go up. This side's supposed to go up, right? That's the idea? So let's just try and, with our finger, trace out what's going to happen. I'm supposed to go up. When I come down to -2, I'm supposed to cross through. I'm supposed to get back to this one, right, and cross through. When I get to the 0 one, I'm supposed to touch or bounce off of it, right? Then I'm supposed to go up and then come back through this one, cross, and then eventually come back and cross and go up. And that makes sense that it'll do that, right? So now we come through with our final graph and put it together. So it's going to go up. It's going to come down, cross through, go up, come here, bounce, come down, cross, and then back up through like that. There it is. Okay, we're done. Question? Yes? Quiz? Is that what you said? What was it? X -2 and 5, right? Why is that not graphing that? Oh yeah, degree 0. Yeah, that'll do it. Okay, there's the graph. Okay, that's what it looks like for real. Can y'all see that all right? That's what it looks like for real. Now, let me zoom in on it just a little bit. You can see that zoomed in. It comes down, goes up, comes through, bounces off, goes up, goes down, back up through, right? That's what the real graph is. We had no idea that this dropped way down here like this, did we? So, oh well. Any questions? It's kind of fun. It's okay. All right, so let me see. I think what would be realistic, what I think I'd like to do is that I've done A, B, C. There's left D, E, and F. I think what I'm going to do is I'm going to do F, and I'm going to let you take D and E home as a take-home quiz to be turned in next time. All right? Everyone got that? You're going to take D and E home. You're going to turn it in. When you turn it in, I expect to see, step A, B, C, D, E, F, the graph, right? Not just a picture and you're done. All the work. Show all the synthetic division, everything. Even if the synthetic didn't work, just cross it out. I want to see everything. And that, if you do these two and turn it in, what you get on that quiz, the way I grade it will be very close to what you should expect on the exam, all right? Because I'm going to be looking for all the little details. All right. One of the habits that I see students get into is they don't make the list of numbers, and they just start with 1 and -1. But they just kind of say, well, I think I'm going to always start with 1 and -1. So I need to see the list. Okay, so let me do this last one. And it's -2x cubed plus 3x squared minus 17x minus 30. All right, step A, do we have a polynomial function? Step B, what's the left and right hand behavior? Left goes up, right goes down. Left goes up, right goes down. That's because the degree is what? Is 3, which is odd. And the leading coefficient is -2, which is negative, right? Less than 0. So, have y'all ever seen that movie, Less Than Zero? Yeah, I figured you would with us. It's an old school movie. It's long, yeah, Robert Downey Jr., like one of his first movies. He's like a major drug addict. Anyway, okay. Not much changed for him in his life after that, apparently. All right. Well, next, X-Intercepts. All right, so here comes the hard part. Not hard necessarily, tedious. What is the first thing I'm going to look for when I'm trying to factor this? GCF. Do you have a greatest common factor here? Don't have an X in the last one, though. So, nope, can't pull anything out of there. Okay, how many terms do you have? 1, 2, 3, 4. Maybe grouping will work. It won't. It won't. Yeah, you're synthetic. So let's make our list. I'm going to look at all the factors of 30. And it's actually a -30, right? But we look at the plus or minuses anyway, no matter what. So plus or minus 1 and plus or minus 30. What's next? 2 and 15. So I don't know where you are, but maybe you need a calculator to try, like 30 divided by 2. Maybe you need to, I don't know. Hopefully you don't. 3 and 10. I'm going to stop when I meet in the middle, right? 5 and 6. Nothing else. We're not done this time, though. because the leading coefficient, the number in front of the x cubed, is in -2. So we're going to have to put a 2 down here and make a list based off of 2. The good news is it's only plus or minus 1 and plus or minus 2. Those are the only numbers that multiply to be 2. Agreed? So now we get our final list.
Sorry, why do we do the 2?
Because it's not a 1. If it's a 1, you don't even care. Okay? If it's something other than 1, you have to create a second list. Okay, so here's what we're going to do to get our final list. We take every number here and divide it by this number first. So what's 1 divided by 1? 1, and then plus or minus, you could get a positive or negative 1, right? So you're going to have plus or minus 1. What's 2 divided by 1? Plus or minus 2. What's the 3 divided by 1? Plus or minus 3. So isn't it initially going to be this list to start? Okay, let me write that list out first. That will always happen. You'll get your original list. But along with your original list, you're going to get some more stuff. Any questions on that? Okay, now we move on. We've done every number up here divided by 1, yes? Okay, I'm done with the 1. Now I'm going to do every number up here divided by 2. So what's 1 divided by 2? 1/2. Oops, plus or minus 1/2. What is 2 divided by 2? 1, I already have that in my list. What is 3 divided by 2? 3/2. I'm not turning them into decimals, okay? What is 5 divided by 2? 5/2, right? So I'm going to continue my list down here. What is 6 divided by 2? 3, I already have 3 in my list. 10 divided by 2? 5, I have that in my list already. 15 divided by 2? 15/2, I don't have that in my list. I'm going to put that here. And lastly, 30 divided by 2, which is 15, which is in my list. So I have, what? Each one of these is 2. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 possible candidates that could work. So I'm going to give you the same instructions on the test. Start with the smallest numbers, but don't do the fractions, okay? So we're going to start in this list right here. We're going to work our way up. Yes? How do I get these two? I took this number here and said, what numbers can you multiply to get 2? 1 times 2, -1 times -2. Okay? You have to do that when there's something other than 1. And we said last class that if this is a 1, then all you have is this case where there's a 1 here, and all of these divided by 1 is the original list. So that's why you don't have to consider it. Okay, let's begin. Synthetic division is our friend. -2, 3, -17, -30, right? No spaces in there? Are you going to have spaces on your homework? Let me see. Are there? Ah. Ooh. Ooh. All right, start with 1. Someone work ahead of me and try and see if you can get something. Nope, doesn't work. Move on to -1. Ooh. What is that? No. Nope. Anybody there yet? Moving on to 2. Damn, come on. That didn't work. So I'm starting to lose hope. That didn't work either. Okay, so I'll do 3. I'm going to go to 3. If 3 doesn't work, I'm going to try a fraction.
I tried 3, didn't
3 and negative 3? Anyone try 5 and negative 5 yet? You tried 5, no go? Negative 5. So the reason I put this in here is because I wanted you to see how a fraction works with synthetic. All right? How does a fraction work? So let's try this. Out of space here, go to a new page. We have negative 2, 3, negative 17, and negative 30. And what was the first fraction? 1/2? Okay, so I put 1/2 out here. Drop the negative 2 straight down. What is half of negative 2? Negative 1. Make sense? Add straight down, you get 2. What is half of 2? 1. Add straight down, you get negative 16. What is half of negative 16? Negative 8. Okay, it didn't work, but do you see how that actually works out? There's probably one like that on the homework. Was there? Yeah, may have been. I don't remember doing it, but if you say so. All right, so what would I try if 1/2 didn't work? Negative 1/2. So negative 2 comes down. Negative 1/2 times negative 2 is 1. Positive, right? Add down, you get 4. Negative 1/2 times 4, so half of 4 is 2, but it's negative because the negative times a positive. So negative 2, and then add down, you get negative 19. Uh-oh. That doesn't work. Half of 19 is not a number you know, and we're looking for it to be a 30, right? That didn't work. I said on your test it will happen within the first few tries. I didn't say that today in class it would happen on the first few tries. All right, so we go again. What's the next fraction I had? 3/2? This will be an interesting one. Okay, so bring your negative 2 down. Okay, what's 3/2 times negative 2? What's 3/2 times negative 2 is the same as negative 2 over 1, right? So you get negative 3. The 2's cancel, and you just get negative 3. Okay, put negative 3 there. Add down, 0. Anything times 0 is 0, so 0 here. Add down negative 17. Oh, no, that's not going to work, is it? Right, that's not going to work. So, yeah. So, yeah, negative 3/2 is what I'm going to go to now. Has anyone got anything to work? I'm just wondering, because I know some of you are like working on your own. Negative 3/2. So you go there, you get positive 3. Add down, you get 6. Okay, so what is negative 3/2 times 6? Negative 9? Negative 9. Add straight down, what do you get? Negative 26. No? No? Yeah, that doesn't work either. No, I'm just checking something here. I thought I made this so it would factor negative 2x squared. No, I'm going to factor it. Oh my goodness. It did not factor. Hold on, something happened when I wrote the problem down wrong. What's that? I thought I checked them when I made the notes. Let's see, did we copy the problem down right? Okay, well, I'm glad I didn't send you home with that one. So what the moral of the story here is not there is a typo in this right here. This is not factorable. Okay? The moral of the story here is that it's possible still, even with this technique, to not be able to factor something. All right? It's possible. And so in a chapter that we're going to head into later, we're going to actually address something like that. Not yet, though. The only way to factor this is if we now bring in complex numbers. So we're kind of stuck. So I don't know what to do here. I can either make another example where it will work, or you get the idea and we can move on. So let's take a vote. How many of you get the idea and we can move on? Pardon? Yes, one is always yes. So one is you're okay, you get the idea, you're ready to move on. Two is no, I need to see an example that worked. Not factorable. That's never going to happen to you on a test, okay? I'll figure out what the problem was with this one. I bet you it's just a sign in here. And I wanted it to be -2, though. So I don't know. Whatever. I'll figure it out. Let me try this. Yeah, it's going to be one of those. There it is. Yep. It's +17. Yep. Okay, so look, maybe we can save ourselves here. You already said you don't want to do this, right? Fix that on your paper to a +17, please. Let's see if any of these would have worked. Well, actually, 2 would have worked. Okay? 2 would have worked. It won't take me long to do it. Can I just fix it real quick? Sure. Okay. So look, this is all foobar here. All right, so we're going to move on and fix the problem to be -2x cubed plus 3x squared plus 17x minus 30. And we're going to go, the same thing happens, left and right hand behavior still the same, right? Let's do this. And let's do what I say would work too. Yeah, try 2 out here. So -2 comes down, that gives you -4. You add down, you get -1. Then you get -2, that gives you 15. No. 15, yes, and then that's 30, and then the remainder is 0. That's the way it was supposed to work. Okay? But you got it a good exercise in how the fractions work. Okay? And then at this point, you just come down. This gives you a factor of what? X minus 2. And then this is what I was really curious to see what you would do. -2x squared minus x plus 15. I don't know how comfortable you are factoring something like this when there's a negative out here like this, right? So what you could do is you could take that negative and factor it out and just put it like a -1 sitting out here, and then change it to a 2x plus x minus 15. So you change the signs, 2x squared. Change the signs of everything in here by taking a -1 out of the whole thing. Does that help? Maybe, maybe not. Okay, so let's say you're stuck on this. You don't know how to factor it. Couldn't you do this? 2, 1, -15? And then continue with your list? Yes? And I'll tell you what works. -3 would be the one that works next. 2, And then what would that tell you the factors are? X plus 3 out here, and 2x minus 5.
How would you know that if it was 2x minus 5, just by getting that plus 3?
How do I know it's 2x and not what?
I don't know. I can do it over there. I can kind of figure it out. But when you come over here and we try 3, I guess you have to figure it has to be negative 5 because you're trying to get to negative 15. Right?
How do I know?
X plus 3, and then how do you get to 2x plus 5?
Are you saying I don't know what you're saying.
I'm sorry.
This method, you're okay with what we did. You're just like, how would you get from here to here if you didn't do this?
No, I got it now.
Okay. I'm going to continue. Negative 1, x minus 2, that broke down to be x plus 3, and then 2x plus 5, or minus 5. There it is. You could multiply a negative 1 in, but it would only go to one of these. It wouldn't go to all of them. So you could make that a negative x plus 2, or you could make that a negative x minus 3, or you can make that a negative 2x plus 5. It does not change your x-intercepts. It has no effect on it, believe it or not. How? We're supposed to set this equal to 0 now, right? Okay, so set this one right here to 0 for me. You get 2x minus 5 equals 0. You move the 5 over, right? 2x equals 5. You divide by 2. X is 5 halves. Yes? Agreed? Now, what if you had moved that negative through first? Your equation would have been negative 2x plus 5, right? Now set that to 0. So you move the 5 over, and it becomes negative 5, and then you divide both sides by negative, and you get positive 5 halves. Same answer. It has no effect. That's kind of weird that it does that, but it's the way it is. Okay, so I know you want to move on, I want to move on, so I'm just going to kind of, yes? No, you could leave it out there. Okay, what are the multiplicities on all of these? 1, 1, 1, 1. So, right, we're going to cross on all of them? All right, so we never pulled the GCF out of the beginning, so our graph would look like this. The x-intercepts are what? 2, negative 3, and 5 halves. So here's negative 3. Where's 5 halves in relationship to 2? Is it bigger or smaller? Bigger. So this would be 5 halves, and this would be 2. What was our end behavior? Left went up, right went down. So it's going to go up on the left, down on the right, and then it crosses through on all of those. Like that. Okay, sorry, I just wanted to kind of fix that. I know I went through that real haphazardly at the end. This is not acceptable for a take-home quiz. This work right here that I just did is not acceptable. A, B, C, D, E, F. Show all the steps. Whatever it is. All the steps. Was it D and E? D and E. I'll double check those after class to make sure they factor. Okay? So if you're at home and it's not breaking down, check your email, because that means it didn't factor. But I'm pretty sure they're okay. All right. So that's it. Polynomial functions, like we have this new way of determining how to graph polynomials. All right, so now when we look at things, we can graph lines, we can graph parabolas. Parabolas are a different technique than this, right? Parabolas, we did the vertex, axis of symmetry, that was a parabola. Polynomials, this process. Now we get to our third to last type of function, all right? We only have 3 more to go as far as the things that we're going to be able to graph in this class. Rational functions, exponential functions, and logarithmic functions. Exponentials and logs are usually easier than the rationals. Rationals are by far the hardest, okay? So, I have notes for you. So here's what I've got. Where did I stop? Right there. Take one, pass it back to that table. Same thing, pass them all the way back. If you have any extras at the back, make sure everyone through the back got those. Good question. There was a question, are we doing 5.2? I'm doing 5.2 and 5.3 all in one section, so I'm just calling it 5.3. Okay? And also another thing, on the 5.2 and 5.3 homework, don't do the 5.2 and 5.3 homework. I'm going to give you a take-home homework instead. What's that? I'm going to need to finish writing it up. I don't have it done yet, but I'll probably send it in an email later today or tomorrow. It's just going to be sketching stuff. That's it. Okay? Okay. So now, we're going to talk about rational functions. You have the handout, right? I'm going to go through things here, and then we're going to have a set of steps. Okay? The steps, this is it right here. These are the steps. All right? Since there's so many steps, I printed all the steps on one page for you, so you can use it as a reference. So that's the rest of the notes.
These are the hardest ones?
I think so. They're the most involved, yep. No. What happens later, what makes things more complicated later is that you run into an issue of things being new, meaning new notation, stuff you've never seen before, and so it's confusing because of the notation. All right. Y'all ready? I need everyone try and pay attention, even though I'm turning the lights off. I'm pretty sure I'm going to allow you to have the steps. I know some faculty are really against giving steps, but there's a lot here. And my philosophy has always been that in the real world, you're not ever locked in a room with no references and saying, you know, go figure this out. You can't go look at a book or, you know. In the real world, you have something to go to, so that's why I allow things like that. So, okay, what is a rational function? A rational function is simply the quotient of two polynomials. So we just studied polynomial functions, right? We know what polynomials look like. If you take a polynomial and you divide it by another polynomial, you get what's called a rational function. Here are some examples of rational functions. So let's take a look at this first one. 3x plus 5 over x squared minus 2x minus 24. You could say that the top is a linear polynomial, right? Degree 1 polynomial. You could say that the denominator, the bottom, is a parabola or a degree 2 polynomial. So we agree that's a polynomial over a polynomial. All right. This one over here, top right, you have a second degree polynomial over another second degree polynomial. So that, again, is a rational function. Here, you have a third degree polynomial divided by a second degree polynomial. So it's a rational function. Here, linear over quadratic again. So first degree over second degree. Those are all examples. I mean, there's infinitely many, right? So we are going to start by looking at a very important rational function. It's the most basic rational function that you can look at because it has a lot of the properties when you look at it that a lot of rational functions have. So we are going to look at 1 over x. Now let's all agree that this is still a rational function. The one on top, is that a polynomial? x to the 0. And 0-degree polynomials are polynomials. So if there's no x there, but there's a number, that still is a polynomial. Divided by another polynomial, x, which is just a first-degree polynomial. You understand? Yes? All right, so let's try and figure out what this looks like. And before I show you the graph, I want you to think about this. What's the domain of this function? Or you could tell me if you'd like what you can't plug in. You can't plug in 0 because you get division by 0, right? So when I draw this function, when I get to 0, I shouldn't have anything, right? Yes? Okay, now let's try and figure out what the end behavior is just by looking at it. As I plug in x's, like let's say I take 1. I plug 1 in there, I get what? Plug 1 in for x, you get 1. Plug in 2, you get 1/2. Plug in 3, 1/3. Plug in 10, 1/10. So what's happening as you go out to the right? The function is doing what? Getting smaller, right? 1/10. You plug in 100, it's 1/100th. Plug in 1,000, 1/1000th, right? Plug in 1,000,000,000, 1/1,000,000,000, tiny little number, right? But does it ever actually get to 0? No, it doesn't. Now let's go the other direction. What if you plug in -1? What's 1 over -1? -1. What's 1 over -2? -1/2, right? What's 1 over 1 over -3? -1/3. So what happens if you plug in -100? So that's pretty far out the left side of the x-axis. You get 1 over -100, which is -1/100th, which is really small, but it's negative, isn't it? So what's happening is, remember on the right, we said it was getting closer to 0, right? But it was positive numbers. On the left, it should be getting closer to 0, but they're all negative numbers. And at 0, what did we say was happening? Undefined. Sorry, that was not the graph. What the hell happened? I have no idea why that's doing that. I know it shouldn't be. Hold on. I've got to change my code, and I don't know if I'm going to be able to recover that. Holy shit. I did something to my code. Let me see. It worked last night. All right. I have a backup. Wow. I don't know what's going on. Hold on. Let me close out the program. One over x? No, I need, if it's a number, it's just going to be constant function. We don't want that. I'll get it. No worries. Y'all just take a break. Think about the beach. Think about the sunny vacation you're going to have here next week. There it is. I don't know what happened, okay? There's the graph. So the blue is the function, all right? We said that as you move to the right, it gets smaller, right? So as I move to the right, I'm kind of following that. It's getting smaller and smaller and smaller, right? Getting closer and closer to 0. If I'm on the other side, I'm negative numbers getting closer and closer to 0. So do you see this dotted line that goes across right here? That's kind of like, what I want you to look at that dotted line as being, is kind of like a magnet. You know, magnets like attract, well, sometimes they repel, but, you know, the idea of a magnet pulls something towards it. I want you to look at this dotted horizontal line as being a magnet that pulls my graph towards it, but only at the ends, okay? That horizontal dotted line is only affecting my end behavior. With me? Okay. Now, at 0, we said it was undefined, didn't we? So notice that at 0, I have this vertical dotted line. And look what's happening. There's some very interesting stuff happening. As my function gets closer to 0, as it tries to go to the right, like this, where does it go? It goes down. It starts taking off way down to negative infinity. Why? Why is it doing that? So let's investigate that a little bit. Our function was 1 over x, right? Somebody give me a number that is getting close to 0 over here. Someone give me a number that's close to 0. Negative 1/10. Yes? Negative 1/10. So if I were to plug negative 1/10 in here, I would do 1 divided by negative 1/10, but that's the same as flipping the fraction over, isn't it? And making a what? Negative 10. So give me something even closer to 0 on the left side. Negative 1/1000. That's even closer, right? Coming in? If you plug that in, what would you get? 1 over negative 1/1000 would give you negative what? 1,000. So does that make sense that as I try and get closer, the graph starts to dive down forever? Yes? Now, what about on this side? If I try and plug in a number as I get closer to 0 from the left side, from the right side like this, give me a number that's really close to 0, but on that side. 1/100th, but positive this time, right? Plug that in, and you get 100, don't you? So it's starting to get bigger as we go closer to 0. How many of you have to take calculus? You're going to spend a lot of time with this idea of graph behaviors as you approach things. Very important concept in calculus, so get used to it. All right. Do I have any X-intercepts in this graph? No. Does that mean you cannot have X-intercepts in rational functions? No, you can have them. This one in particular, you do not. Okay? Do you have any Y-intercepts in this graph? No, but you can have them. The main two characteristics that I want you to see with this graph is that we have this vertical dotted line, and the way that I like my students to look at this vertical dotted line as like a vertical barrier, okay? This is a vertical barrier, and as you try and draw your function gets towards it and goes like, what do I do? You know, and it doesn't know what to do, so it can't bust through the barrier, it has to go somewhere, so it just it dives down, all right? On the other side, same thing's happening, you get close to it, it's like, and it goes up forever. Does that make sense? We need to figure out where this vertical dotted line came from. Where did it come from in our function? Here's our function. Where did it come from? That vertical line has an x-coordinate of what? What's the x-coordinate of that vertical line? 0, right? And what does 0 do to this function? It makes it undefined. So maybe with all rational functions, whatever makes the bottom undefined is where we have these things happening. And that is exactly it. Okay? Now, this dotted line that goes horizontally does not act the same way as the vertical one. The dotted one horizontally only affects your end behavior. That's it. And it acts like a magnet, and it pulls the curve towards it. With me? Okay. Now, that's just one specific example of a rational function. So what I'm going to do now is give you some more to look at. So I'm going to put this one in here. 3x plus 5 over x squared minus 2x minus 24. 3x plus 5 over x squared minus 2x minus 24. Here we go. Holy shit. Okay, we got a lot going on here, don't we? Let's start with those. Where would we start? Let's start with X-Intercepts. Do we have any X-Intercepts this time? Yes, it looks like we have one right there, don't we? Now notice that the graph went through that horizontal dotted line. Okay, that's critical that you understand. The horizontal dotted line only affects what? The ends, okay? It's not a barrier, it's a magnet. So it is okay that we went through like that. So it looks like we have one X-intercept. How about vertical barriers? Vertical barriers. How many do we have? 2. Where do they look like they're happening? Looks like at -4 and 6. Well, here's the original function, right? Look at the denominator as a polynomial, quadratic, right? You could factor it into these two factors. What makes these two factors 0? 6 and -4. Oh, -4 we have vertical barrier, 6 we have a barrier, right? So it's going to turn out that any time our denominator is 0 is where we're going to have these vertical barriers. With me? All right. How about the X-intercept? Hard to tell what it is here. But remember, X-intercepts come from when your function is 0, right? If you look at the top here, if you just look at the numerator, 3x plus 5, and you set it equal to 0, what would you get? -5/3. That's exactly where that one is. Okay? Y'all with me? Okay, so recap. Vertical barriers seem to be happening when you have the denominator 0. X-intercepts seem to be happening when your numerator is 0. This horizontal thing seems to be always the x-axis. I wonder if it's always the x-axis. I doubt it. All right, so we're just, again, looking at characteristics of these things. Let's look at the next one. I'll do the top right one. X squared minus 4x over 2x squared minus 16x. 2x squared. Was it -2x? No, 2x squared minus 16x. Here we go. Oh, man. Well, we got something else happening here. Let's start with, what should we start with? How about the verticals? The vertical barriers. Let's start with that. It looks like 8, right? And then look at the denominator here. 2x squared minus 16x. When we factored it, one of the factors was x minus 8. So if you to make this factor 0, you plug in 8, right? Why? But what about this x right here? What about it? We should have, I mean, if we follow what we've been saying, we should have another vertical at 0, shouldn't we? Do y'all see that? Why don't we? Do you see something else? I'll see if anyone catches it. That's right, because you have an x on the top also. And this x over this x cancel each other out. Do you see that? But what we have at 0 is something bad, because you cannot plug 0 into this function, because you would get 0 divided by 0. 0 divided by 0 is undefined. So what we have right here, you can barely tell, what is that? It's an actual hole in our graph. Do you see it? It's a little, I put a little orange dot there so you could see it. Do y'all see it? So we have to be careful that we don't get in the habit of just going, oh, when's the denominator 0? Oh, 0 and 8, so I draw vertical dotted lines. Because sometimes it'll cancel out and we'll have a hole there instead. So we're just looking at characteristics right now, okay? We're going to have a whole set, a method of figuring this all out. How about x-intercepts? Do we have any x-intercepts? Looks like at 4, look, that top one right there, that would make that top 0, right? Why don't we have an x-intercept at 0, though? Because it canceled, right? That's why it doesn't come into play. This can be tricky, isn't it? Can you kind of see that? This is going to be a tricky thing. Now, the other thing is that dotted horizontal line, that magnet line. It used to be the y-axis, right? It's been the y-axis this whole time, or not the y-axis, the x-axis, yes? This time it's what? It appears to be moved up a little bit, doesn't it? How do we know that it's moved up? I'm saving that, okay? Yes, question? Where? You factor an x out first, or factor out a 2x first. If you factor out a 2x, you're left with an x minus 8. If this x had not been here, right, if that x wasn't there, then it would have been a difference of squares. All right, so we got a lot going on. Let's see, next one, x plus 4 over x squared minus 16. So if you take x plus 4 over x squared minus 16, you factor the bottom, right? So let's take a look at that. The bottom is 0, right? The bottom is 0 at 4 and negative 4. So you would think we should have two verticals, but we only have one at 4. At negative 4, well, that's a common factor with on top. So we should have a what there? A hole. So at negative 4, we have a hole. Do you see the hole in the graph? Okay. What about an x-intercept? It would have to be at negative 4, right? But you have a hole there. So you can't have an x-intercept there. How about the horizontal dotted line? It's the x-axis. Okay, so I hope that those 4 examples just gave you kind of an idea of the complexity of these things, all right? Just how crazy they can actually be. I'm making one up now. So there's another one. I'm just making them up, okay? The horizontal line is going to have to do with the degrees of the top and bottom. Okay, so are y'all ready to get into it now? I mean, this is just a visual representation of what's happening. Let's get into the notes now. We got about 25 minutes. Okay, so here are some properties of rational functions. They're continuous on their domains. Continuous meant that we can draw it without picking up our pencil, all right? But we're saying continuous, you can draw it without picking up your pencil on the domain. Of course, where it's not defined, you can't draw it. So notice that in this picture, this blue part, it's defined here. So when I draw it, it's nice and continuous and smooth. Yes, it's taking off, but I'm still got my pencil on the paper, right? Until I get to this vertical dotted line, that's where I have this weird barrier. I have to pick my pencil up there, but that point's not in the domain, so I don't count that. Once I get past that vertical barrier, this blue part's nice and continuous and smooth. This part over here is nice and continuous and smooth. With me? So that's the first characteristic of rational functions. When you draw them, they're not going to be jaggedy or anything, all right? The next one, they may have x-intercepts. They may not. Second thing, they may have a y-intercept. They may not. The third thing, they may have what we call vertical asymptotes. Vertical asymptotes. This is a weird word, asymptotes. 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 Just say it fast, no one really cares. All right? I will abbreviate those VA from here on out. These are those vertical barriers. Okay? This right here is a vertical asymptote. This right here is a vertical asymptote. We also may have horizontal asymptotes. That would be this horizontal dotted line that acts like a magnet, right? And you may have holes. All of these say may have, may have, may have, may. You're not guaranteed any of these. So we have to figure out each one of those, don't we? Do we have them or not? Okay, so this can be pretty complicated. So we put together a nice set of steps to do it. I don't know what the book does about this. This is my set of steps. I've been doing these for years. So if you go to the book, you're not going to find these steps. All right? All right, first of all, step A, what we've always done, make sure you're looking at a rational function. Step B, completely factor the numerator and denominator. Remember when we were looking at the ones just now, I had them all factored and you can kind of see things cancel or whatever? We have to be able to do that step. So factor everything, top and bottom. Step C, very important. Look for common factors. Common factors were like when we had the x plus 4 on top and bottom a second ago, or when we had those x's. If you have common factors, cancel them out, but remember you're going to have a hole there. Okay? You're going to have a hole. The next thing after we figure that out is to find the x-intercepts. To find the x-intercepts of a rational function, you simply set the numerator equal to 0. That's all you have to do. Solve it. That's whatever your answer is, are points on your x-axis. All right? Next thing, find the vertical asymptotes. Those are those dotted vertical lines. To do that, all you have to do is set the denominator equal to 0. After you get the solutions to that, those are your vertical dotted lines on your graph. Those vertical lines will force your function up or down. You do not cross those lines ever. Do never draw your function through the dotted line, vertical one. After you've done your vertical asymptotes, you now do your horizontal ones. And this we haven't talked about, like how you can determine where they are. Here's how it's done. There are 3 cases. There's 3 cases for the horizontals. First case, you look at the degree of the numerator and denominator. If the degree of the numerator is bigger than the denominator, this is backwards. Hold on. This is backwards. Oops, glad I caught that. Less than. This one is greater. Please check. Please change on your notes. If the numerator's degree is smaller than denominator, then the x-axis is going to be your horizontal asymptote. Okay? If the numerator is smaller than denominator, degree. If the numerator's degree is bigger than the denominator, make sure you change that on your cheat sheet thing, then you're not going to have a horizontal dotted line. It's not going to be there. Which means, as you'll see in a second, we're going to have to figure out what happens then. If there's no magnet pulling our function down at the ends, what does it do? Right? We'll have to figure that out. Case 3, if the degree of the numerator and denominator are the same, they're equal, then what you're going to have to do is look at the leading coefficient of the numerator, divide that by the leading coefficient of the denominator, whatever number that is your horizontal asymptote. Okay. I'm giving you the steps. We're, of course, going to work through an example. All right. Remember, horizontal asymptotes of a rational function is a dotted line that I recommend you only draw at the ends. It acts like a magnet, pulls your function towards it. If you don't have a horizontal, right, if you don't have one, then your function will act like a polynomial. That means it's going to do like this sort of thing at the ends. Okay. You can tell I'm putting you all to sleep. Part G. After you've figured all this shit out, you plot all the information on your graph. You put it all there, okay? And you would think that would be enough. It's not enough, okay? So plot all informations, part A through F. Use this information to determine what I'm going to call test points. Test points should be between each x-intercept and vertical asymptote. You also need one test point at each end. You then evaluate the function at these test points and plot your results. And then finally, you put it all together with a nice continuous function, and you do not forget the holes if you had them. That's it. Easy. You think you can probably just do that right now on your own, right? Just do a quiz. We'll just have you graph one. All right. Come on, it's not spring break yet. Right, it's only Tuesday. We have one more day. Let's do this first example. What? What's wrong? You didn't want to do it? 3x plus 5 over x squared minus 2x minus 24. Hey, look, if anything, please at least feel happy that I'm going to give you the steps on the test. Because I know some instructors don't give you the steps, and so they ask you to sketch a rational function. You have to just remember all this stuff. All right, here we go. Step A. Is this a rational function? Yes, it is. It's a polynomial divided by a polynomial. Step B. Were there any extras? Oh, wait, you know what? I think I printed it out and put it in here. Oh, I have them right here. Never mind. Got it. Okay, step B. Completely factor the numerator and denominator. So I'm going to rewrite my function. The numerator, 3x plus 5, is already a linear expression, and it cannot be factored any further. Right? 3x plus 5 is 3x plus 5. The denominator, however, is a quadratic trinomial. You can factor this using AC method, or if you don't know how to do it with the AC method, you now have what? Synthetic division. So you could write all the factors of 24, and then you could create this list, and then you could look out here, it's a 1. You could say, hey, great, now I can do my little thing and get a 0, and you're done. But that would take a lot more time, wouldn't it, if you don't know how to factor? Negative 6 and positive 4. It's completely factored, right? Step C. Oh, wait, no. Step B. Completely factored. Yeah, step C. Look for common factors. If you have them, cancel them out. Remember, you'll have a hole at whatever x value makes the factor 0. Do we have any common factors? No. Step C, check. Done. No holes. Okay? I have no holes in this graph. I don't cancel anything out. Isn't that nice? Step D. Yes, we'll do the next example. We'll have a hole. All right? Step D. Find the X-Intercepts. So I set the numerator equal to 0. That's it. X-Intercepts. Set the numerator equal to 0. I trust you can solve that. X is negative 5/3. What is this going to be on my graph? What is that going to be? An X-intercept. That's a point on the x-axis, right? I'm going to write that next to it because you start to lose track of what all this stuff is. This is a point, right, on the x-axis because it's an X-intercept. Step E. Look how quick we're going through these steps. Find the vertical asymptotes. How do you find the VAs? Always do what? That's the HAs. You set the denominator equal to 0. Now, when I say that, you set the denominator equal to 0 on part B's one. Okay, that means, remember we could have canceled factors? If you had canceled them, those are gone. And so you don't look at those in this step, which in the next example you'll see what I mean. But in this case, our denominator is this, right? Set them both equal to 0. That was minus 6. Set those to 0. You get two answers. X is 6 and X is negative 4. Now, what are these on our graph? What do those look like on our graph? Those are our vertical dotted lines. Yes. Barriers. They're like barriers, right? Now, keep in mind, the vertical dotted part is not technically part of the graph. It's there to help us. But if you just have a computer graph these things, it won't draw this dotted stuff. I did that to help you see them. Okay, we're done with the verticals. Now the horizontal. So this is F. Okay, so for horizontals, we are going to compare the degree of the numerator and denominator. So tell me real quick, what's the degree of the numerator? What's the degree of the denominator? 2. Then, what case are we working with here then? The degree of the numerator is 1, denominator is 2. So this is where I had the mistake on your page, right? The numerator's degree, 1, is smaller, right, than the denominator's degree, which was 2. So we are in case 1. With me? The highest power of x, is your degree, right? So when I'm looking here, the numerator, you look up here. The highest power of x you have up here was 1. The highest power of x you have on the denominator was 2. That clear? Yes? Okay. So now we are in case, I'm going to write down case 1. And what does case 1 tell us our horizontal will be? The x-axis, or y equals 0. Y equals 0, right? Y is up and down. Y equals 0 is the x-axis. Okay, I'll come back. Or the x-axis, whatever you want to look at it as. Y equals 0, the x-axis are the same thing. It's a line. Y equals 0 is a horizontal line that has a y coordinate of 0 for every point. If you go back and just do a review on vertical and horizontal lines, if I write x equals 2 and I tell you to graph it, it's a line that goes through 2. If I write y equals 2, it's a horizontal line that goes through a y value of 2. So if I write y equals 0, you move this thing down 1 to 0, and it's through there. Does that make sense? Y equals 0 is the x-axis? Okay. That wasn't convincing, Case 1, if it's case 1. All right. All right, part G. Man, this ain't so bad. Part G. I need to put all this information on a graph. And I would also recommend that you this might be your final graph, this might be your first draft. It just depends on how things go for you. So, give yourself some space. Okay, let's go and plot all this information. So the first thing we ever got was an X-intercept. The X-intercept was what? Negative 5/3, which is about what? Negative 1.66 something. So if this is negative 1, negative 2 would be here. I don't know. It would be somewhere about in here. Y'all agree? That's my X-intercept. What came after the X-intercepts? Vertical dotted barriers. Where were those? 6 and negative 4. So let me go to negative 4. Negative 3. Negative 4. I'm drawing a vertical dotted barrier. Dot, 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 dot. Dot, 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 dot. And then I do the same thing at positive 6. 1, 2, 3, 4, 5, 6. Dot, 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 dot. Dot, 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 dot. Does anybody remember me talking about why in the world it is that we have to do this? Like, why are we here? What are we doing? Well, if you're engineering, you need this stuff because you need to totally understand how rational functions behave. But in the big picture, for people going into other fields, it's about procedure. Can you follow a procedure? This is a very long procedure here. Can you follow directions? Right? And then, of course, along the way, there's math involved, but overall, are you the type of person who can follow instructions, come up with the result, or when someone gives you a set of instructions, you're just like, can't do it. I can't do it. Nobody's going to want to hire somebody who can't do that. So, you know what I'm saying? You get the idea? I mean, that's what I think, right? The degree, the college degree means you're teachable, right? You're teachable. I can teach you how to do the job I want you to do. All right, so here we go. That's the verticals. What's next? What was next on our? We're plotting all the information A through F. Right now I have D. I got the X-intercept. I've got E down. How about F? Did we have any horizontal asymptotes? The X-axis. This was our dotted line that was a magnet, right? But I said it only affected the ends. Yes? So what I suggest to you is you only draw the dotted parts at the end. See my red dotted stuff over here? I shouldn't put it in red, but it's going to stay in red. I did not draw it all the way through. On my program here, I drew it all the way through because it was easier to code that way, okay? I just said draw a friggin' line. I didn't want to cut it off. So it was just too easy that way. So for you, I recommend you only do the ends. Why not go all the way through? Because historically, people are going to think that if they see a dotted line coming through here, that they can't cross it. But you can. The dotted lines going horizontally are the magnets. They have no effect on the inside of the graph. With me? Someone's going to go to a tutor. The tutor's going to draw it all the way across. And it's going to mess you up. So if you go get tutoring, tell them, my teacher told me only draw it at the ends because it does not affect the inside of the graph. Right? Okay. I can always tell on the test who got help tutoring because the horizontal asymptote's drawn all the way across. All right, anything else that we have as far as information? D, E, F, it's all there, right? So we've plotted all the information. What's the next thing? Plot all the information. Use this information to determine what are called test points. The test points should be between X-intercepts and vertical asymptotes. So let me go back to my graph. I need to find a point, any point I want, but the point has to be between the X-intercepts and vertical asymptotes. So here's a vertical, right? Here's an X-intercept. Somebody give me any point between here. -3. I'm going to put a little cross on it. -2 would have worked also. Put a little cross on it. The reason why I'm putting a cross on it is because I'm not saying that's a point on my graph. I'm saying I'm about to go plug -3 into the function and see what it spits out. Somebody, let me see. I have an X-intercept here. I've got the test point between those two. How about between this X-intercept and the next vertical that I see? 1 would work. What else would work? 2, 3, 4, 5. 0 would have worked. -1 would have worked. Right? Any of those. So which one do you want? 1? Okay. 1 was the first one I heard. I personally would have done 0 because I like plugging 0 into functions because usually it's nice. Okay, so I'm going to plug in that. Let me label it below it 1. And so I've got a test point between this X-intercept and this vertical. So there's no other verticals or X-intercepts in the middle that I need to find a test point for, right? Nothing? But it also says in the notes, also, that doesn't make sense. Also, you need 1 test point on each end. Also, you need 1 test point on each end. So let's go look at the end of our graph. So I need a test point on this end. Anything you can think of over here? 7? Put a little X there, 7. And then something on this end. -5. So how many test points do we have? 1, 2, 3, 4. And what am I supposed to do with those test points? Plug them into the original function. And then plot those points on my graph. That should be all the information we need to draw it. Okay, so let's do this. I'm going to be evaluating, let's see, f of, it was a -7. I'm going to be doing f, no, not -7, it's -5. I'm going to be doing f of -3. I'm going to be doing f of 1 and f of 7. You ready to plug in -5? Yeah? Man, I'm almost out of time. Crap. Okay, that sucks. Okay, so here's the deal. When I say plug in -5, that means you plug it in here, correct? Now, if you're clever, which I want you to be, you could also say f is this, isn't it? So you could plug -5 into this instead, and you get the same result. That's the one I'm going to go into. What, -5? It's going to go in the whole thing. The whole thing. Everything. Okay, so let me plug -5 into this. Help me out. So, and watch this, okay? Pay attention. 3 times -5, -15. Plus 5, -10, right? -10, watch what I'm going to do down here. Next page. Watch what I'm going to do. Right here, I'm going to put negative on top. But that's a negative sign, and I'm circling it. I actually don't care that it's -10. Okay? I don't care it's -10. Then go and plug -5 in right here. What's -5 take away 6? -11. Again, I don't care that it's -11. I just care that it's negative. All right? Now, the next thing, -5 right here. -1. Again, I don't care that it's -1. I just care that it's negative. The reason why I don't care is because 2 negatives on the bottom multiply to be a what? Positive. So I have a negative on top and a positive on the bottom. A negative divided by a positive is negative. What this tells me is that when I plug -5 in and I go to plot the point, it is below the x-axis. And that's all I care about. It's just like with the polynomials, we didn't know how high and low they went. I don't care how high and low this thing goes. I just care that it's below the x-axis. You with me? Now, if you want to go find the actual value, go for it. But this is much faster. All right, so here we go. Now watch what I'm going to do. At this -5, I'm going to come out here. I'm just going to draw a point anywhere I want down here. I don't care. There it is. You know, I'm going to use green. I'll make my graph green. There. Okay, now I plug in -3. Let's see how quickly we can get -3, because I'm out of time, officially out of time. -3 on the top here would give me what up here? Negative. -3 here. Negative. -3 here. Positive. Negative times positive. Negative. Negative over negative. Positive. So that means that when I go here, it's going to be above. You have to let me finish. There's no way I cannot finish this. I'm sorry. Okay, when you plug in 1. 1 here, positive, 1 here, negative, 1 here, positive. When you multiply a negative and a positive, you get negative, positive over negative, negative. So we're going to have a negative, so it's going to be below the x-axis. So I can already hear you saying, look, there's a pattern. Negative, positive, negative, right? It's not always going to follow that pattern. Or else we wouldn't do this. Okay, then you plug in 7. Now it will be positive, all right? Okay, everyone understand that? Okay, now I have to draw the picture. As high as you want, okay? This is the most critical part, all right? I know you want to go, and you actually could walk out on me. I don't care if you do. But we are at the very end. This is where you have to think the most critically about everything. At the end of the day, you have to draw a function. Has to pass the vertical line test. Has to be continuous, so you have to draw it without picking up your pencil, except for at these barriers. I'm going to start at this point real quick, and I'm going to imagine that the graph must be drawn to the left of that point, to the right of that point. Okay? To the left, what has to happen? Why? You've got a magnet. It's pulling your graph towards it, isn't it? Yes? Okay, to the right, as I try and draw it to the right, there's a vertical barrier. Vertical barriers make it freak out and want to go up or down. Which way? Why? Because it looks like it's going to go down? What would happen if I turned up? Right there, what did I just do? I created an X-intercept. I only have one X-intercept. So by process of elimination, it has to be down. So I just draw it like this. Now I do have to pick up my pencil. I go to the next point, and I do the same thing. To the left, what happens? To the right, what happens? So to the left, got to go up. Can't come down, can't cross here. So it's got to go up. Then from here, it's got to go here. So we're back in like kindergarten at this point. It is truly connect the dots from here to here. And then it's got to go to here, right? And then as it moves along here, it's like, da-da-da-da, what does it have to do? It's got to go down. Can't turn up because it would have an X-intercept, right? So it's going to look like this. Oh, sorry, my hand slipped. It's going to go like this, and then it turns down like that. The vertical's in my way, so it comes down like this. Yes? And now you jump over, pick up your pencil, go to this point, draw to the left, got to go up, draw to the right, magnet. We're done. Okay, so we will pick up where we left off. Check your email. I'll send you home a couple of, maybe one problem like this to try on your own. But the quiz, don't forget the quiz, those 2 problems. Thursday? No, we're going to do some more of these. I think we'll have an in-class. We'll finish this up, and we'll have an in-class where you can just work on a couple. Have a great day.